Raise your hand if you're sick of Miss Butler's videos. Raise your hand if you are starting to wonder if Miss Butler owns any professional clothing or only wears Legend t-shirts. Want to know the cool part? I can't see you, so I don't know if you raised your hand or not. Okay, if you're sick of me, that's okay. We are going to have Mrs. Stewart, Mrs. Osowski, Mr. Vasco, Mr. Charvella. They're going to be making videos too. I just got these first ones because they're my favorite topic to teach. Am I lying? You don't know. Anyways, okay, we're going to do measurement today. There's a few extra learning targets on your Cornell notes, but for the most part, we want to be able to measure in chemistry accurately and precisely. So we should probably know what accurate means and precise means. You might think you know, or you might think they're the same thing, but hopefully I can prove you wrong by the end of this video. All right, so my first question for you, what is the difference in the marks on a volumetric pipette? So that's this guy that we'll use. We actually pull liquid up into here and then we can drop it into, so if I'm transferring from one container to the other. So I want to know the difference in the markings on this guy, so you can see 0, 1, 2, extra little tick marks. Maybe I need like a, there, that's a little better. You can see the markings compared to a graduated cylinder. Graduated cylinder we also use to measure liquids. This one has 2 sets of markings. So on one side it actually counts backwards, similar to the pipette. Let's see if I can get to it. I want like a black piece of paper. So that says 70, 80, 90, or we'll actually use this side where it counts because we fill from the bottom up. Okay, so you can see 10, 20, and the markings, those tick marks for 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, sorry if it's flipped on my camera. So first, what are the difference in the markings? I want you to add that answer into your notes. And then why might I choose to use this volumetric pipette? Let's say I need 10 milliliters, 7 milliliters. Why might I use this guy where it has markings for between 8 and 7, so 8.1, 8.2, 8.3, 8.4, 8.5, 8.6, 8.7, 8.8, versus this guy where it would only have markings at each one, like 11, 12, 13, 14, 15. Okay, I'm talking about the markings here. So again, less about that I'm asking for 10 and this guy starts at 10. I'm saying, why might I use this even if I needed 20? Why would this be better to use versus this guy based off the markings? Write those answers, what you think, in your notes as a prediction. All right, so the United States is weird, if you haven't figured that out yet. And we measure things a little differently. We measure things in like inches and feet and miles. But the rest of the world, including the scientific community, uses a measurement system called the metric system or the SI system. The SI system, SI stands for Le Système International d'Unité. I took up to French 5 and a year of French in college, and that's the best I got. So if you take French or you're Mrs. Pickles and you're watching this for some reason, I am so sorry. Starnes, sorry. Okay, but we're going to use the metric system in this class. So things like centimeters, meters, liters, milliliters, right? We're going to avoid things like ounces. We're going to avoid things like miles in this class. Okay, first of all, I understand this is high school and you are a smart person, but you would be shocked when I say, hey, go get the mass of this, and a kid tries to put it in a graduated cylinder like this, right? Or if I say, hey, go measure the volume, and a kid puts it on the balance. Okay, so again, I understand you're an intelligent human being and you know what length and volume are, but I've seen it before from kids your age, so I just want to make sure we're all on the same page so you don't look a fool in the lab, okay? So length, if I need you to measure the length of something, it's the straight line distance between 2 points, and we measure in meters. If it's smaller, we can do millimeters. If it's bigger, we can do kilometers, right, instead of miles. Mass is the amount of matter in an object, so how many particles are in the object, and we measure that in grams grams, or if it's bigger, kilograms, or if it's small, milligrams. But usually for our class, we're going to use grams because we use a balance to measure mass. So in our class, when we use something that looks like this, that is called a balance. It is not a scale, it is a balance. And then obviously we use a ruler to measure length. I kind of skipped over that, okay? Volume is the amount of space an object or a chemical takes up, or the capacity of a container, right? So a lot of times we're gonna be measuring the volume of liquids, but if you've taken geometry yet, or you did 7th grade math, you know how that you can take the volume of an actual object, length times width times height for a cube, right? So, but for our class, we're gonna use probably liquids and measure the volume. We will be measuring in milliliters or liters. So milliliters is usually something in a graduated cylinder, but if it's a lot of liquid, maybe liters. And then just so I don't make your math teachers mad, if we're doing length times width times height, we might use centimeters cubed as well. Centimeter cubed as a unit for volume. This guy is called a graduated cylinder. We will use that for measurement, and I'll explain why that's the best tool for measurement in a little bit. Okay, weight is something you might be used to. We're not going to deal a ton with weight in this class. That's more physics, but it's the force at which gravity pulls on matter. So yes, it involves how much matter there is in an object, but it also involves gravity, which is why physics kind of takes over, and you'll learn about weight more in physics class, but that's measured in newtons, so capital N for newtons. Your scale at home probably measures in pounds, right? But so we're not going to really deal with pounds in this class. Other helpful units for the SI or the metric system, time will always be measured in seconds. Temperature, there's 2 units for temperature we use. It's going to be Celsius, degree C, or Kelvin, just capital K, no degree sign for Kelvin. Notice we're not going to use Fahrenheit in this class, either Celsius or Kelvin. And on the left-hand column of your Cornell notes, you should have a practice problem. It says convert 32 degrees Celsius to Kelvin. This is the easiest equation you're ever going to learn. If I give you a temperature in Celsius, all you have to do is add the number 273. So in this case, Kelvin is going to be equal to the Celsius, which I told you is 32, plus 273. So 32 plus 273, that should give me 305. And the unit is K for Kelvin. I'm going to box that answer so you know. Notice my answer has a number and a unit, capital K for Kelvin. Okay, if you dozed off on me, wake up, let's go. This is new information. You have not been taught this before, and I wish they taught it earlier because then I wouldn't have to untrain you, okay? When you walk into chemistry, most kids, they just measure, right? I'm going to give you this. You're just going to look at it, tell me how much liquid is in there. You got to eyeball a little if it's between the lines, okay? I give you this, same deal. You're going to eyeball if it's between the lines. But there is a proper way to measure because you can't be a liar. There's no lying allowed in this classroom. I need you to be honest, and science needs you to be honest too. How good is your lab equipment? So here's what we do. First of all, if it is non-digital, meaning it doesn't give you a reading, like a balance gives you the reading. It's a digital tool. Some thermometers you plug in and it just spits it out, right? If you've been getting your thermometer taken at Legend when you walk in every day, they put it to your forehead and it goes beep and it tells you can turn and see the actual number spit out on a digital reading. If it is non-digital, you are going to record all digits you are certain of and one estimated digit. Well, what does certain mean? Certain means there is a marking for that digit on the device. For example, this graduated cylinder right here. I need the dark. Oh, green. You think I would have figured this out between the slides already, but alas, here we are. Perfect. All right, I'm gonna go to this side. If we look, without the glare hopefully, there are markings for every 1 milliliter. So we go from 10 up to 20, those are the big lines, but then we also have, teaching during a pandemic, right? Okay, then we also have a marking for 1, 2, 3, 4, 5, 6, 7, right? Every 1 milliliter. So I am certain of the ones place, right? 11, 12, I am certain of that. And then I'm going to estimate 1 digit past. So let's say I have a reading and I think it is 12 milliliters. Well, I am certain that it's 12 because it's right on that line or maybe a little past. And then I'm going to estimate 1 further. So maybe I think it's halfway between the 12 and the 13, 12.5. Maybe I think it's actually right on the money. I think it's exactly 12. I'm going to say 12.0. So always, when it's non-digital, everything you're certain of plus 1 estimated digit. You can't do more than 1 estimated digit. That's lying. That's saying you have a better measuring tool than you have. Always, though, you do 1 estimated digit. How do I actually measure volume if I have a graduated cylinder like this? Here's what you're going to do. You're going to put the graduated cylinder on a flat surface. Check. You are going to get eye level with the meniscus. What is the meniscus? Well, when you put a liquid in a graduated cylinder, like water, for example, it's going to have a slight curve, and it might not be as exaggerated as what you see right here. The bottom of that curve is the meniscus. So I need my eye to be at the bottom. That's not the bottom, Butler. Good try. Let's try retake 2. Right there. So I need my eyeball right there. I don't want to be looking from up here or from down below. That's a bad angle, we say in softball. Bad angle. Okay, so let's look. I'm going to pretend the water line is to here. I'm not going to hold it up in the air. That makes it tilted. What a waste of time. Put it down. And I need some knee bend, people. You got to bend your knees a little bit. Mr. King can teach you how to do some good squats in strength and conditioning. Highly recommended. But we are going to get to eye level of where the liquid is. Not up above, not down below. Eye level. Look at the meniscus. You're going to record all certain digits plus 1 estimated digit. Okay, that was kind of complicated. Let's take it back a notch. Digital equipment, a balance, a digital thermometer, anything that we might use that plugs into a wall or has a battery in it. The device estimates the digit for you. So you only write down what the balance says. So if a balance says 35.3 grams, you write down 35.3 grams. Do not estimate an extra digit. The balance already did that. All right, let's practice. So the first one, I have a centimeter ruler, and we're going to measure the length of this red bar. So remember, we record all certain digits. So can we all agree that this red bar is at least 3 centimeters? It's between 3 and 4. So I am certain, because there is a marking on the device, for 3. I am certain that it is at least 3, so I'm going to write that down. Are we certain of any more? Well, yeah, we have more markings. It's not just the 3 and the 4. There's 3.1, 3.2, 3.3, 3.4, 3.5, 3.6. Maybe it's somewhere, I think it is 3.7, okay? 3.7. We are certain that it is 3.7 because there's a marking for that on my device. Are we certain of more? Are there markings between 3.7 and 3.8? No. So that's going to be my estimated digit. So I'm certain of the 3. I'm certain of the 7. Certain of the 3, certain of the 7, because there's markings for those. And now we have to estimate a digit. 1 past. That's what science has agreed upon. So I think it's maybe a little past 3.7, so I'm going to say 3.71 centimeters. What if you're like, no, Ms. Beller, it is right on the money, 3.70 centimeters. That's your estimated. You estimated that 0, it's right on the money. What if you're like, no, it's exactly between 3.7 and 3.8. I'm estimating that. What if you're like, Miss Beller, you need to get your eyes checked. I don't think it's all the way to 3.7. I think it's 3.68, right? I think it's actually, that's estimated. We're just before the 3.7 or 3.69 maybe. All of those would be accepted. So that last digit is kind of in a range. And obviously when we're kind of close to the 0.7, right? Are we on it? Are we a little before? Are we a little after, right? Sometimes this is subject for debate as well, the 0.7 or the 0.6, but notice it's a high 0.6. You didn't say 3.60, right? You're almost to 3.7. So there are a lot of acceptable answers, and it's usually around that estimated digit. What would be wrong is if you said 3.7. That is not acceptable because you did not estimate a digit. Let's look at the beaker. What am I certain of? Well, if you look at the markings, I have a marking for every 50, right? This one is at 100, this one 150, this one is at 200. So I am certain that we are somewhere between 150 and 200. But there are not markings for every 10. There aren't markings for every 20 or every 1. So I am certain that we have at least 100. Am I certain of the tens place? Well, we have a marking for 50, but we don't have a marking for 160, 170, 180. So this is where we're going to estimate a digit. So I think maybe it's 180 milliliters. Maybe you would say 170 milliliters, but our 7 and our 8 are the estimated digit. We are only certain of really the 100. Same thing for this Erlenmeyer flask. We have markings on this guy every 50, right? 150, 200, 250, 300, 350. So I am certain we are at least at 300, but I don't see markings for 310, 320, 330. So I'm going to estimate that we are maybe at 320 milliliters. Could I say 325? I think it's exactly between. No, because then that's your estimated digit. You're lying about how good the device is. You can only say 325 if there were markings every 10. So this is your estimated digit. That 0 is just a placeholder because 32 makes no sense. All right, for some reason my picture got cut off here. So I have a graduated cylinder. This is the full view of all the markings, and then I zoomed in as if there was a liquid, a meniscus right here. So this is the zoomed in. So what you can see is there are markings every at 10 and 20, and then we also have 1 milliliter markings in between. I'm saying milliliter because it's a liquid. So I have a marking at 11, 12, 13, 14, 15, 16, 17, 18, 19. So I am sure that it is somewhere between 10 and 20. I am also sure that it's 15, 16, 17, 18, right, for my eye level of this meniscus. So I'm certain that it's at least 18, right? Because we have the marking for 18. Did I estimate a digit yet? No. So let's see, is this meniscus somewhere between 18 and 19? Sure, I think it's 18.6 milliliters. You might say 18.5, 18.7, 18.3 milliliters. That is fine because it's the estimated digit that we have a little bit of wiggle room. So in chemistry, it's very important to be both accurate and precise, but there's a difference between the two. Accuracy is how close a measurement is to the actual value. So it's basically how right you are. If you put something like this on a balance and it says it weighs 10 kilograms, that's way too heavy. Something is wrong, right? That's not very accurate. So if I want to be more accurate, what do? Well, first, you need to read devices correctly. Like for this guy, okay, if I have a liquid in here, I need to make sure I'm putting it on a flat surface, getting to eye level, right? Because if it's crooked, that's not very accurate, right? You could also choose the best tool available, right? So make sure that if you, for example, are measuring a tiny, tiny amount of liquid, this might not be the tool to be most accurate in. Maybe you need a smaller graduated cylinder or something like the volumetric pipette. And then if it's a digital tool, you need to make sure it's calibrated, it's working properly. Okay, so accuracy is just that we're using what we have correctly. Precision, though, is two different things. One, how close measurements in a data set are, how close they are to each other. So if I do 10 trials, are we getting similar results with those trials? Or it's how many significant figures there are in a measurement. It's how many digits there are in a measurement. Right? Remember, we measure all certain digits, the ones that are markings, plus one estimated. So a better device, like this guy, this is more precise because there were markings every 0.1 milliliter, is more precise than this guy because there were only markings every 1 milliliter. You get more digits with this one when you do all certain and one estimated, less digits with this guy when you do all certain and one estimated. So if I want to be more precise, you are going to choose the device with more markings, right? This guy has more lines on it, every 0.1, than this guy, every 1 milliliter. The beaker is the absolute worst because it only had markings every 50. So beakers are great for storing liquids, but they're not great for measuring liquids. We're always going to use a graduated cylinder. If I say you need 25 milliliters, we're going to use this guy instead of the beaker. If I say you need something less than 10, we would use this guy because there's better markings even than the graduated cylinder. So it's a measure of how much are you measuring. Something between 10 and 100, we would choose this guy. Something between 1 and 10, we would choose this guy. And also how many markings they have. I know there's nothing worse than a video within a video, but I need you to pause the video, go to Canvas, or go to your Cornell Notes, there's a link, and watch this short video. I promise it's good and covers this information. I wouldn't make you watch 2 videos if I didn't think this was the best one out there. So seriously, pause this video, go watch the other one. I'm doing the same just to refresh my memory, remind myself of how good this one is. All right, so hopefully you watched the video. So the first situation where his crossbow was not calibrated correctly, he had his correct form, but something was wrong with the crossbow, and so he was hitting the target below the apple, right? But it was all clustered, and so this would be an example of precise, because they're all clustered close together, but not accurate because it wasn't on the bullseye. In the next situation, William's hand had a tremor. He was very nervous. Okay, and so he had a bunch of random shots not clustered together, right? But sometimes he hit the bullseye. So in this situation, this shot right here is accurate. That one was accurate, it hit the bullseye, but it was not, but as a whole, looking at all 5 of those, not precise because they weren't clustered close together. One bullseye was accurate, but not precise with those 5 arrows. All right, so hopefully you can anticipate what precise and accurate would look like. It would be clustered together, all in the bullseye. Perfect. All right, hopefully this was helpful. I promise we'll have practice in class on how to measure and how to estimate that digit, and you'll have an opportunity to ask any questions. Good work.